Hey learners, Jared here, and today we're going to start discussion on what is, in my opinion, the most difficult, most elaborate type of problem that you can encounter, and that's a rotational collision problem. But stay with me so that we don't lose any momentum. Because in order to solve these, you're going to have to utilize the conservation of momentum to figure all this out. Just like our discussions with linear momentum conservation, we're going to apply the same techniques to an angular momentum type collision or anti-collision, as we've been talking about. First, let's talk about something that isn't necessarily a collision at all, but just a change in our moment of inertia while an object is rotating, or like the figure skaters, or Jude and Harvey on a swing. Notice that when they pull their mass in, they start to rotate much faster. Angular momentum is your moment of inertia times your angular velocity. Notice it's analogous to translational momentum, which is translational mass times translational velocity. As they bring their mass in, their moment of inertia decreases. While that moment of inertia is decreasing, in order for angular momentum to be conserved, an equal increase in your angular velocity must take place. There aren't any outside forces present that would cause this angular momentum to be siphoned off or lost to somewhere to the surroundings. So as they decrease their moment of inertia, their angular velocity increases proportionally. Now, as that happens, it takes work on their part. It's hard to pull your mass in as it is spinning around. And in so doing that, their momentum is staying the same, but their kinetic energy is actually increasing because they are doing work. They're having to pull their mass in. That's a change in kinetic energy, an increase in kinetic energy. Now, what if you have something that is a collision type problem? That is, you have something come in and it hits and it causes a rotation. To start, we're going to look at objects that are fixed in place, that are only free to rotate. They aren't free to rotate and translate. In a problem like this, where you have mass coming in and hitting an object causing a rotation, there's a couple of things that we have to take into account. One, what is free to happen? In this example, our object that is getting hit is only free to rotate. It's locked at some hinge, some axis of rotation. Because of that, translational momentum isn't going to be conserved for the point mass hit object system. But because it is free to rotate, rotational momentum is going to be conserved, and that's what we're going to look at first. Key factors for this type of problem: the mass that's coming in and colliding with a stationary object. How far is it from the axis of rotation? What is its mass? And how fast is it moving? The moment of inertia for a point mass is just mr squared. What is its mass? How far is it from the axis of rotation? And then that value squared. It's tricky to think about rotational momentum being conserved when the object coming in is moving linearly, but it is moving off that axis of rotation, and because of that, it actually has angular momentum. There's angular momentum before the collision, and there's angular momentum after the collision. The angular momentum for a point mass is that I omega. It's the exact same as it was for a rotating body. I for a point mass is mr squared, and the angular velocity for that point mass is just your velocity divided by that radius, as what we talked about previously in the rotational kinematics video. What that simplifies down to is your mass times your velocity times your lever arm, or how far you are from that axis of rotation. That value is going to be our initial angular momentum, and that's what we're going to use to figure out what is going to happen after that collision takes place. If our initial momentum is a certain value, then our final momentum has to be equal to that value. Now, if the mass that is colliding hits and sticks to that object, then the combined mass is what we're going to look at rotating. The two are going to rotate together. So it's still I omega initial equals I omega final, But now our moment of inertia has changed because we've added mass to our rotating object. The moment of inertia for this new object is just the moment of inertia of what was initially there, plus the moment of inertia of the point mass. Once we have that new combined moment of inertia, we can solve for our final angular velocity, or if that was a known quantity, we could backtrack and solve for what was the initial velocity of the point mass. Thank you guys so much for watching. I hope that gets you started on angular momentum type problems. We'll look into collisions where the object is both free to rotate and translate next. And as always, keep learning.